Okay, probably we can start now. So just to verify whether my audio is working fine or not, could you just let me know if it is fine? Could able to hear me properly? Hello, could you hear me? Okay, yeah, thanks. Okay, so probably we can start now. Last time we were discussing some topic about quantum entanglement, and thereon we also discussed some. One of the interesting case of EPR paradox. So we just started that, but then we couldn't find the time to finish it off. So probably we can continue that maybe in some extra session that we will be having in future. So yeah, yeah, during that time we will surely will finish that discussion. So fine. Okay. So Uh, so today's topic will be on the quantum particles in presence of some external magnetic field. So we'll see how quantum particles evolve or how quantum particles behave in some external field. So particularly magnetic field that we will look onto. So why is it so like magnetic field like it's very interesting to study. We know like we have been talking about spin a lot like over a few weeks, and it's really an interesting feature of every quantum particle that they have a very peculiar or a very inherent property within them that gives rise to various different phenomena, and one such we will look right here in our discussion today as well. So that is when we consider a spin particle. So a spin particle in the sense when we are talking about in the context of quantum mechanics, so we are talking about some quantum particle having an intrinsic angular momentum. So, for example, what are the particles that we or that comes to our head when we think about quantum particles having spin? So it's mostly electrons, protons, or other particles. So it's mostly, you generally think of charged particles. Like charged particles are basically you'll find found in nature them having spin half is one of the fundamental uh, is one of the fundamental what you say uh, uh, the along with like charge and mass that you try to identify a fundamental particle that you give for every fundamental particle uh, there is some fundamental attributes to them like either in terms of mass, charge or spin. So that is what how we identify fundamental particles. So we'll look into their charge, mass, or spin, and depending upon that, like we come to a conclusion that this is the particle with a definite or with a unique set of values, and there are other particle with other unique set of values, and yeah, that is how you track all quantum particles. When we are talking about uh, quantum particles in presence of a magnetic field, it's basically will be mostly the charged particles we'll be discussing right here. So charged particles, why is it so? If you think of charged particles having some, let's say, angular momentum or a charge or some charged particles going around a loop of some conductor, or you could recall yourself about your previous lessons on I mean, on your previous lessons on uh, electric current going in a some circular loop or whatever, any kind of loop that you were trying to calculate its magnetic field due to that current loop, or more things you have done that in the past. So those things, if you would see, in the context of what we will discuss here, is something quite analogous that that will also exist in the current framework. So, for example, as I was telling, so when a charged loop, when if you consider a current loop, you see that there you find a magnetic dipole moment, because that is what happens. Like whenever a charged particle in motion, you obviously get some magnetic field, but when it goes around a loop, you see some magnetic dipole moment associated with that current loop. So similarly, when I talk about um, spin particles, or spin particles having charge like an electron. So an electron which has a negative charge of minus c, and then it also has a spin half. So if you consider that electron, so that electron can be treated as, or can basically uh, has a intrinsic magnetic dipole moment, or some sort of intrinsic magnetic dipole moment is also associated with that electron when we talk about a spinning particle, a spinning charged particle. So that is what we will try to see, because that is the idea how, like, a spin, like a charged particle, having some angular momentum, a charged particle going in some loop or something, like we used to have magnetic dipole moment. So that is magnetic dipole moment from the actual motion of charged particle, going around some loop or something. But now we have a spin. So due to the spin, the charged particle also has a intrinsic magnetic dipole moment. So that is something like quite I mean interesting when we talk about intrinsic angular momentums of quantum particles, because this is something naturally comes. Uh, once we lay down the principles of quantum mechanics, like we say there is a fundamental property associated with every particle that is spin, then all these are consequences. So it's just remarkable, and right. So we'll see, like, how we can see those things. So to understand, I'm sure that this thing is also well, I mean, talked about by the instructor. You can find in the lectures which are already uploaded. So I think it's a week ago or something. So yeah, there were surely some discussions about Lamar precision, and spinning, or spin off particle having charge like electron in presence of some constant magnetic field, or also time varying magnetic field. So you have seen all that. Like we'll go over them in a brief review once again, and we'll see some related problems as usual what we do here. So right. So uh, let's take the simple case at the beginning. So where um, um spin half spin half particle at rest in uh, in a constant or uniform external magnetic field. So right. So as I was telling you, I mean, a charged particle is quantum charged particle. So a quantum charged particle means it has some spin. So that due to that spin, it also or basically some intrinsic magnetic dipole moment is also associated with that spinning charged particle. So how can we define that magnetic moment? So recall once again your electrodynamics from your basic electrodynamics. You can write down magnetic dipole moment for a charged particle having some angular momentum. Magnetic dipole moment for a charged particle. So the charged particle, uh, let's say that it has some charge q. Uh, for a charged particle having mass m and uh, and angular momentum L. So right. So there is this what is known as gyromagnetic ratio. So uh, like from electrodynamics, from from standard electrodynamics, we know gyromagnetic ratio is defined as. So right, this gyromagnetic ratio is defined as uh, magnetic dipole moment mu equals to or basically magnetic dipole moment and angular momentum. The ratio if you take the ratios of their or rather ratios of their magnitude, you will get something uh, q over 2m. So this is something classically you write. So classically, and this magnetic moment is basically something q over 2m or L. So or basically you can write it's up to some uh, negative sign or a factor of 2 or half. So this is something classically which we know. So and this result is basically verified for I mean this is for only constant magnetic field. This ratio is valid for a particular constant or uniform magnetic field. And yeah, and right, this you can always prove this gyromagnetic ratio from the basic definition of magnetic moment. So in similar I mean in the similar analogy or the if you draw this analogy in the context of the quantum spinning particle, which has instead of the angular momentum, now it has a spin. So with that, like I can say, like uh, so this is true from the basic definition of of mu. So right. So similarly in quantum mechanics we have, so similarly in quantum mechanics we have uh, mu equals to uh, gamma s, where this gamma is minus e over m. So, yeah, so this is the intrinsic magnetic moment associated with any spinning charged particle. So, just like classically in classical electrodynamics, how you have a magnetic dipole moment basically comes when a charged particle having some angular momentum, or as I said, like some uh, uh, like we can give some examples right here. So charged particle going in a charged particle moving in a conducting loop, or charged particle, or a rotating charged sphere. So all this, I mean, classical examples of charged particles or moving charged particles having some magnetic dipole moment. So, in contrary to that, or like in drawing that analogy in the context of quantum mechanics, so a charged particle itself has an intrinsic angular momentum. So that intrinsic angular momentum will eventually give rise to intrinsic a magnetic moment, which we are writing right here. So an electron which has a spin half, it has an intrinsic magnetic moment, which is mu equals to gamma s, and gamma is basically its charge over mass ratio, and s is the spin half for the electron. So yeah, and like also classically you have seen to define energy, or the basically the uh, electromagnetic energy associated with a magnetic dipole moment. For that you you can recall this relation, like you probably would be using something, some potential energy notation as minus mu uh, dot b. So classically, that is you write the magnetic electromagnetic potential energy. So again, borrow the similar idea in the quantum mechanical context. So where we will define Hamiltonian as something h. So this Hamiltonian will be some operators equals to minus gamma uh, b, uh, or or basically yeah, it is minus mu dot b, that is equals to minus, if I write mu as gamma s, so that will be gamma b dot s. So that is the Hamiltonian for a charged particle, for a spinning charged particle in some constant external magnetic field. So if it's a spinning charged particle, like let's say electron or a proton, if it is kept uh, in some external constant magnetic field, so this will be the Hamiltonian, will be that will be associated with it. Just like how energy is associated, which we know classically, with a spinning with a charged particle going in a loop in a external magnetic field. That will be the energy that how we define. So in the I mean, drawing that similar idea in the context of quantum mechanics, that is how I write the Hamiltonian as well. So now, if we exclusively write down like what would be the exact expressions for this Hamiltonian, and if this is the Hamiltonian, then what would be the states? So that is what we do in quantum mechanics. So if a Hamiltonian is defined for a given system, then we write the state of the system. So right now our system is just an electron in some external magnetic field. So you have seen systems, so many systems, like over the days, since you've been studying this quantum mechanics, like you have been talking about the a particle trapped in an infinite well, or a some harmonic oscillator system, a particle subjected to some harmonic oscillator potential, like half kx square. So for different potentials or Hamiltonian, you have seen different systems, and you have solved the systems using Schrodinger equation. Their states you have calculated, uh, right? So uh, uh, yeah, you have done like all this exercise before. Mm. So similarly, yeah, just a minute. Okay, so yeah, I was talking about the Hamiltonian right here. So then you can write the Hamiltonian as something following. So uh, we know, let's consider the magnetic field as let's consider this magnetic field as, so this is S, right, is in some z direction, and then take a spin, uh, and right, and we'll consider the spin in some, let's say, uh, in some z direction. So we'll take the sz basis. Uh, so it's a spin-off particle again. uh, so the we can write the in like in matrix form. uh, Hamiltonian will be, or yeah, so or you can denote it some, because these are operators this time. So minus gamma d0 sz operator, and this we can write it as uh, minus gamma d naught h bar by 2 1 0 0 minus 1. So sz again here I'm using, this is your uh, Pauli matrix, so which we have also seen last time around in our last discussion. So it's your third Pauli matrix for a spin-off quantum particle. Like you can define these Pauli matrices. So yeah, and you see, you have already defined a Hamiltonian for your system. So also you have written down in the matrix form. Then you can evolve this system. So that is what we've been looking into when you are trying to study some quantum system. So and it's a not a very complicated system, like because I mean, your Hamiltonian is not time dependent. So it's a time independent Hamiltonian. So you can use time independent Schrodinger equation, or the yeah. Let's say that you want to calculate the state of the Hamiltonian. So you consider something. Let's say chi will be your chi is your uh, or basically yeah, let's say this is your initial Hamilton. So initial states, initial eigenstate of the Hamiltonian will be, so there are some chi plus. So chi plus will be basically you have to basically take so this is your uh, right. So if this is your Hamiltonian, this is Hamiltonian matrix form. So the eigenvectors will basically give you the states of your for the given Hamiltonian, for the given quantum particle which is in that Hamiltonian. So we know the eigenstates of this matrix already. We have seen it like quite many times before. So like 1001. So the eigenvectors are 1001 with this prefactor. So that means that is your total eigenvector. So that is, I can write down as something uh, or basically yeah. So your eigenvectors are 10. This is our eigenvector and its corresponding eigenvalue. Eigenvalue we know for 10 it is plus h bar by 2. So we write uh, h bar by 2 plus h bar by 2, and then you see uh, with your Hamiltonian you have um, so h bar so eigenvector of let's write down eigenvector of h bar by 2 1001 is 1001 uh, and eigenvalue is plus h bar by 2 and minus h bar by 2. So that is what you know. So using that, like I can write uh, my eigenvector and eigenvalue for the given system. So right, so this is your first eigenvector. Corresponding to that, you have uh, eigenvalue including the prefactor will be uh, right. Including the prefactor will be minus gamma b naught h bar by 2, and your second eigenvector, its corresponding eigenvalue will be plus gamma b naught h bar by 2. So for corresponding to second eigenvector, you have minus h bar by 2. So minus h bar by 2, when you multiply with the prefactor which is already having negative sign, so that becomes your plus gamma b naught h bar over 2. So yeah, so that is your initial eigenvectors. But when you evolve the systems, to evolve the system, use according to for the time evolution, for the time evolution of your quantum system, you use Schrodinger equation. So use Schrodinger equation minus I s bar del chi of some at some time t del t equals to h chi. Then chi t is basically is quite easy because you'll just have to integrate it. I mean, um, or I mean, we write this chi of t as some linear combination of the eigenstates. So you can write that as let's you can write that as some a chi plus uh, exponential of minus I uh, e plus th bar plus b chi minus I. This will be uh, yeah, minus I e minus t of h bar. So where e plus and e minus are basically or so let me just write this as e plus and e minus. So this is your uh, e plus and this is your e minus. Okay. So this is your how you define your state. So again, in matrix form, you can write the state as a exponential I gamma b naught t over 2, then b exponential minus I gamma b naught t over 2. So use chi plus and chi minus, which we have written, and using e plus e minus values, you can write this in the column vector. So that is how you define your state in some time when you evolve after some time t. So initially, chi is just simply this 1 0 or 0 1. It would be either 1 0 or 0 1. But then when you evolve this, so it will be mixture of 1 0 and 0 1 with some expansion coefficients to each of this term, right? So then so basically here the point is like I wanted to see a very interesting uh, like phenomena happens here. So let's consider if this t equals to 0 at t equals to 0 chi 0, you can write that, you can see it will be something ab. So uh, so if initially it can be also in some superposition state, it depends when you measure the system. So once you measure the system, it will be either on chi plus state or chi minus state. So but if your system is left idle, it would be a linear combination of those eigenvectors. So yeah, at t equals to 0, you have uh, I mean your initial state is just a b column vector, and and we know like for any um, eigenvectors, it demands me that it should be orthonormal. So that means my chi 0 should uh, be normalized. It should be some identity vector. So suppose if I choose a equals to cos alpha by 2 uh, and b equals to cos alpha by 2, then you will see that my uh, this linear combination will satisfy or basically this, I mean normalization will condition is basically satisfied when I am choosing a equals to cos alpha by 2 and b equals to cos alpha by 2. So there's a physical reason to that, like why you can choose like this, and I mean what's the significance of uh, I mean picking your prefactors a and b, or your expansion coefficients as cos alpha over 2 and sine alpha over 2. So this is sine alpha over 2 sine, right? uh, Fine, then you can write your state, your So this is your chi of t at some uh, chi of t at some time t. I mean, your chi of t is your eigenvector when you evolve your system at some time t. So uh, that is how you get this exponential factors uh, attached to each terms. So like that is normally how you do for a time independent Hamiltonian system. Like when you evolve the system, so these are the exponential factors that you get when you evolve them. So yeah, so I mean, it's just simply like for example, as we have seen previously, uh, if if you define del psi or del t as some h psi, then um, your psi is basically exponential minus I h over h bar t. So this is I h bar psi. So this is psi 0 at psi 0. Then uh, if your psi is something a phi 1 plus b phi 2, then your psi of t, so this is psi of 0, so this is psi of t will be some a times uh, uh, so this is psi of t, right. Yeah, you're right. This is some exponential. You basically operate this minus this a phi 1 plus b phi 2. Yeah, then finally you get something psi of t as uh, a times exponential minus I e1 over h bar t phi 1 plus b times minus I e2 over h bar t over phi 2, where e1 e2 are your eigenvalues for corresponding phi 1 and phi 2. So yeah, I mean that is the same idea, like just applied here. So it's not something very too much technical here. It's just straightforward. What happens to your state when you evolve in time. So this is your time evolution of a of some constant Hamiltonian. So that you have seen in, in many other places, like your particle trapped in a infinite well or harmonic oscillator, whatever you have seen so far. So, so getting that idea only, we are writing down the Hamiltonian for the, we are writing down the eigenvector for this Hamiltonian, for the spin-off Hamiltonian in constant magnetic field. So this chi of t finally it becomes, which we have written down here, with a b writing down the exact form cos alpha over 2, um, uh, cos alpha over 2 exponential I gamma b naught t over 2 sin alpha over 2 exponential minus I gamma b naught t over 2. So yeah, this is your chi of t. So now just finally, uh, the thing that we wanted to see here is basically following. So if you take the expectation value of this pin, I mean, like for example, when you evolve your system to some time t, you take expectation values of you take expectation values of Hamiltonian, or what is the energy, or basically some angular momentum, or other physical observables. So you want to know, let's say, spin at some time t after when you evolve the system. So the state is given to be this. So find the expectation. So if you take the expectation value of x component of the spin in the given state, so you basically will take uh, chi of t sx, and so you basically sandwich your sx operator between chi of t. So conjugate of chi of t and complex conjugate of chi of t and chi of t. So once you do that, like I mean, this is just a matrix multiplication. So use chi of t here and use sx operator and use this chi of t. So this is chi of t dagger. This is chi of t, and this is Sx operator, so which is given as you recall again. We have seen this before. This is again one of your Pauli metrics. Pauli metrics, and so if you use this, you will find this Sx to be something uh, of h bar over 2 sine alpha uh, cos of gamma b naught t, and sy you will find out as h bar over 2 cos alpha. uh, so I'm you will follow the same process. Here basically your instead of x6 you write down the matrix form of sy, which is again one of your uh, Pauli matrix. So in that case you will get for if you take the expectation of sy, you will get minus h bar over 2 sine alpha sine gamma b naught t. And finally, if you when you write down for expectation value of sz, that is basically h bar over 2 cos of alpha. So if you so these are like you can think of this as three components of your spin vector, and if you basically plot them, you will find I mean at some given point, let's say if you plot it as right. So let's say this is your z-axis and this is y and this is x. So you will find that your spin vector, right? So this will be your spin vector or expectation of spin vector. Uh, that is as you go on time, it basically like this is making some uh, let's say yeah, this is making some angle alpha with the z axis, and you will see that at some time if it is uh, so I'm basically plotting this all the three components of spin vector in some Cartesian three-dimensional Cartesian uh, let me uh, yeah. So yeah, so this what I'm trying to say, this is basically rotating. So it is like making by making some angle, it is actually basically going. So I have drawn this as at some time t, let's say uh, uh, s at some time t. But you see that like this s vector, it moves with as you evolve on time because it is dependent on time. This is time dependent. So at t equals to 0, it would be something cos. I mean cos 0 is basically 1. So it's sine alpha. So it would be in somewhere in xz plane something. So yeah, it would be probably in something in xz plane. And then if you evolve t equals to from 0 to further, if you go on gradually evolve, So this will keep on uh, like moving around by making some angle with z-axis. So it will go like this. So that is what the thing that we wanted to draw here. So what happens if you keep uh, a spinning particle, a spinning quantum particle, in a external magnetic field? Let's say the external magnetic field is constant magnetic field, a uniform magnetic field, is given in some particular direction. Let's say in z direction. Your magnetic field is constant along z direction, and you put another spin particle. You will see that that spin particle will basically will precess over time as we evolve the quantum system. So that quantum system is basically a spin particle in this constant magnetic field. Then the spin particle will basically precess. So that is what this idea is about. So yeah, so that is happens when you have a this uh, uh, any spinning quantum particle having some charge uh, in some constant magnetic field. Now we'll see so if I mean there's any issue or anything problem, or you can speak. Is there any problem or everything's clear? Is it clear or okay? So fine. So now we'll see. Now we'll see like what happens if this quantum particle is kept uh, in some time varying magnetic field. So we'll follow this on. I mean, let's take this the same spin-off particle, let's say electron again, with some gyromagnetic ratio gamma at rest in a static magnetic field B naught K. So, so basically, we are considering the same scenario once again, the spin-off particle as we just talked about, with some gyromagnetic ratio gamma. So the thing which I just said here, the gyromagnetic ratio is gamma, which comes from the magnetic moment when you calculate that. And you remember that this is more, as I was telling, this is this spin vector is basically rotating about about zx about z-axis by making some angle alpha. So that rotation frequency is omega. So that omega you can write it as gamma b naught. So with this gamma frequency, we call this as uh, Larmor frequency or precision frequency, precision frequency or gyromagnetic frequency. So why is it so? It's like think of I mean it's, you can think of this as some kind the spinning particle. You can imagine something kind of a gyromagnetic or like a gyromagnet, like a spinning top. So if you take a spinning top and you think that spinning top is some a quantum particle uh, having some spin and charge electron, having some spin and charge, some plus e or minus e, whatever, any charge. And if you keep that quantum spinning top in some magnetic field, constant magnetic field, in directed along z-axis, then that spinning top will basically wobble. So, like when you give a torque to spinning torque, it rotates. But uh, but if you put that spinning torque and you think that spinning torque is some quantum particle, you will find that that spinning torque will basically wobble instead of like moving just simply like this. So it will basically like wobble. So that is something very peculiar in the context of quantum mechanics. So this is something which you may not find in classically. Like I mean, like you take some classical charged object, and it has, if it has some angular momentum, and if you keep it in I mean in presence of constant magnetic field, you won't find such effects. So it's basically purely manifestation of quantum effect. So like we are moving on to the different case where like with this given setup, which whatever we discussed uh, just moments ago, I mean the uh, constant magnetic field case. So what we are doing on that, so this is what we found. So when you keep the spinning half particle with some gyromagnetic ratio gamma at rest in a static magnetic field of B naught K, then you find that spinning charged particle was basically precessing, well, basically like that the idea which we were talking about for a spinning top, which it wobbles. So that is basically precessing at some normal frequency omega 0 equals to gamma B naught. Now a small transverse RF field. So this is something radio frequency, radio frequency. So some different frequency magnetic field you are giving, which is time dependent. So which is basically some oscillating magnetic field. So you are giving some oscillating magnetic field on top of whatever you had B naught K. So you are now giving this oscillating magnetic field, which has two components, which is both X and Y components. So on top of this B naught K, which was already there, you're giving some time varying magnetic field. So now your total magnetic field becomes this. You have X, Y, and the constant usual or the existing constant field along the Z axis. So right. So now we'll see. Again, we'll start by writing down what will be the Hamiltonian. So right, uh, like write down the Hamiltonian for this scenario. So for this scenario, so you the basically your magnetic field has changed. So with the new magnetic field, you write down the same way how we wrote the Hamiltonian. So again, follow the procedure that we did in the last case. That is Hamiltonian will be again minus gamma B dot S. So this definition will still uh, hold true. So and now your magnetic field has three components, so it will be minus gamma Bx Sx plus By Sy plus Bz Sz. And again, you can write down all the three Pauli bases. You have Pauli matrices for Sx, Xy, Sz. So use Pauli matrices. Using Pauli matrices, you can write minus gamma h bar by 2. So you have Bx and so I've taken h bar by 2 from like the common factor from all the Pauli matrices. So then you have 0 1 1 0 plus B by 0 minus I 0 plus Bz 1 0 0 minus 1. Yeah. So then and also use B what is bx given in the question bx by bz. So So using that, you can write your uh, Hamiltonian as something uh, minus gamma h bar over 2 as b0. Then you have brf cos of cos omega t minus plus I sin omega t. Then so yeah, brf cos omega t minus I sin omega t, and your last entry would be minus by b0. So earlier you had the Hamiltonian when you had just constant magnetic field was simply yeah was simply this Hamiltonian. So this was your earlier Hamiltonian, which was just simply uh, having some diagonal elements non-zero and the off-diagonal elements were zero. So now you see when you are giving on top of this constant magnetic field, you also introduced some time varying or oscillating magnetic field with some radio frequency omega. So with that additional magnetic field, you have x and y components also along with the existing constant z direction magnetic field. So due to which you also have some non-zero off diagonal terms. So that is what we found here. So yeah, so if you take this uh, I mean brf to be zero, which means the radio frequency magnetic field amplitude, then you will get rid of this off diagonals, and then finally your Hamiltonian will basically reduce to your former case, which we found initially at the start of our discussion. So, which means basically you are removing the additional magnetic field that we are giving right here. So, yeah, so just to ensure that things are working. I mean, consistently. There is no drastic things taking place right here. So yeah, but then things will go on to change as we see, because this time when you evolve the system, it's not going to be as straightforward as what we found there. We have to properly calculate the states by time evolution. So yeah, we'll see how right. Then the next thing is to uh, check the following. I mean, if chi of t is a of t and b of t, so which we also did last time. So chi of t is some state for the given Hamiltonian at some time t. So it was basically some linear combination. So let's say is the spin state at some time t. Then show that a dot is I over 2 omega minus I omega t b plus omega naught a. Then b dot is I over 2 omega minus I omega t a. This will be minus of omega naught b. So, so your big omega is basically defined to be gamma brf. So that is a field amplitude, and um, right now, so you have to show basically how a dot is this and b dot is this. So again, as we did in the last case. Just follow the same uh, process once again, where we use the Schrodinger equation to time evolve the system. So because we want to know what is the state of the given system for the given Hamiltonian at some time after some time t. So if you start with the Schrodinger equation, so you can write again del chi over del t and h over chi. So from here you can write del chi as some a of t and b of t. Then you can write your Hamiltonian, the matrix which we got just seconds ago. That was b naught, and yeah, we can further write this as uh, you notice this from Euler relation. You can write this as exponential I omega t, and this is exponential minus I omega t. So this is more compact way to write. So yeah, so using this matrix, we can write the Hamiltonian as P naught B R F E exponential I omega t and B R F exponential minus I omega t, then minus P zero. So and again, your yeah A of t and B of t. Right. Okay. Yeah. So there was small correction. Probably when I was talking about here, like I said, this is yeah. So this will be not psi naught. Like that was my mistake. So yeah, I mean, you get this psi of t, but when you put t equals to zero, then you have psi of t zero. Psi of t equals to zero is basically psi naught. So if this is your psi naught, then you can write your psi of t is this. But this thing is not valid uh, if um, if we are considering this current time dependent Hamiltonian, because that was true only for time independent Hamiltonian. So that we cannot write that. So first let's write this case what we were subjected to write. But so we are intended to write this just simply these two equation. I mean we are intended to prove this a dot and b dot. So from here you can just simply take the derivative. You will find this a dot. You can write it as exactly what it is given here. So you will find that minus h bar from both sides. You can uh, cancel out the common factor from both sides. So yeah, your a dot is basically you can write it as I gamma over 2 p naught a. So if there's anything not clear, like please let me know. Then plus brf uh, exponential I omega t b. Then yeah, this is what something given I over 2 omega exponential I omega t, then b plus omega naught a. So yeah, so your omega naught is basically gamma b naught, and gamma BRF is your big omega, and that is what was basically asked in the question to prove. So similarly, you can write down what is B dot. So yeah, so the next thing which we wanted to know, what would be the case when you evolve this. Uh, so let's write down uh, the the general solutions for A of t and B of t with initial values a0 and base 0 can be written as A of t is something a0 uh, so a0 cos of omega prime t over 2 plus I omega prime a0 omega 0 minus omega plus b0 omega, then sine omega prime t over 2, and have to create a bit of space here, so I can drag this right here. Yeah, so this is multiplied with exponential of I omega t. So you see this very complicated form of A of t and B of t. So uh, B naught will be B naught cos of omega prime t over 2 plus I omega prime uh, B naught omega minus omega naught plus A naught omega, then again sine omega prime t over 2 exponential minus I omega t over 2. So this is over 2, where so you have to show this. So this is true. So so this is true. You can see. I mean, this is not as straightforward as it was before when we were uh, doing this time independent Hamiltonian. So when we had only constant magnetic field, so our Hamiltonian was time independent. But now it is not because of this. Uh, I mean, because of this time varying field. We have introduced a time varying field right here which is varying upon time. So now our Hamiltonian is time dependent. So the idea that we were basically using initially, I mean this thing, uh, this idea is no more valid here. So we cannot write this way. So maybe uh, yeah. So now to prove this, like what we can do is we can use the same. So we have A dot and B dot, which we have calculated. Uh, so this is calculated from Schrodinger equation. So from Schrodinger, from time dependent Schrodinger equation. So this is what we have seen. So from this two expression, we have to calculate what is A of t and b of t. So you can see that these are two coupled differential equations. So coupled differential equation, to solve, you have seen in you probably have seen this in mathematics, in your mathematical methods course, or somewhere in mathematics related with solving differential equations. So when you have coupled differential equations, the first task is to decouple them. So to decouple them, you can take one more derivative. So if you take one more derivative on the first and second equation, you get something a double dot equals to I over 2 and omega I omega, then yeah, omega ei omega, sorry. So you get something of this type b, then uh, yeah, so then there will be b dot plus omega naught a dot. So then you can use uh, right. So now from here, what you can do, you can use this b dot and a dot from here, and you will find that uh, I mean you will reduce this differential equation only in terms of this a of t. And similarly, you can double differentiate the second differential equation. You will get b double dot and something on the RHS. Again, use uh, a dot and b dot. Uh, Finally, you can also make this b double dot differential only in terms of b of t. So there will be only b of t means it should, the final differential equation will be something. You will have two differential equation, one only in terms of a double dot. So a double only in terms of a, so involving a double dot, a dot and a, and the second differential equation is something involving b double dot, b dot and b. So and then you calculate from this. So basically you will get something a of a double dot plus b of a dot plus c of a equals to 0, and similarly you will get something uh, a prime of b double dot plus b prime of b dot plus c prime of b equals to 0. So you can solve this second order ODE. So these are basically second order uh, ODE. So we'll see this particularly explicitly for a particular scenario, maybe in some in one of our future problem. So, but here I can directly try to prove this statement, that we have to basically prove here that these are basically your solutions for a of t. So when you solve this a of t, b of t from here, if you solve from this differential equation, solve a of t and solve b of t, you have to basically get these two results. So yeah, or otherwise we can also prove this in the following way. So what you can do here, we can directly use. So basically what we can do, you take derivative of this equation, this solution which is given, which means you will have some a dot, uh, you will have basically something a dot of t on the left hand side and right hand side. After taking derivative with time, you have something on the RHS, and then you compare the RHS with the a dot. which we have earlier proved, or earlier we have shown right here. And on comparing A dot and on the left and right, you will find that they will match. They will, those two are basically equivalent. So or rather they should be equal. And then that is how you show that this A of t is really the solution for this given Hamiltonian, because we have proven this A dot. So using this A dot, we will prove that A of t, which is claimed to be the solution, that it should be the solution if we use A dot dA by dt from our previous result. So so to do that, you take time derivative of the A of t, the solution which is given. So so that will give you uh, taking time derivative of A of t. So one way is this solving this coupled differential equation. You decouple them. So so basically these are decoupled decoupled form. These are your decoupled forms. So after decoupling, you can solve this differential equation explicitly only on terms of A of t and its derivatives, and this is only in terms of B of t and its derivatives. So you can solve as this is a quite a I mean second order differential equation. But there is one more like very I mean quite simpler way to prove this, because we have to prove that A of t and B of t, whichever whatever is given, they are the solutions. We can use the previous result to show that. So to do that, like let's go back to the A of t and B of t, which was given in the question. So take time derivative of that A of t. That means you are taking a single time derivative. So you have A dot equals to minus so yeah a, A of t is given to be yeah. So if you take time derivative on the RHS, the from the first vector of first term, you will get minus omega prime a0 sine omega prime t over 2. Then right uh, yeah. Then from there you have minus I over omega prime a0 uh, omega 0 minus omega, this complete factor you have, plus b naught omega. uh, then you take derivative of this sine term, that will be omega prime over 2 cos omega prime over cos omega prime t over 2. Yeah, and this is whole multiplied with, so I have to create a little bit of space here. So exponential I omega t over 2. Then the other term is simply just a I uh, omega by 2. So uh, let me see this if this is let me check this for Yeah, if you take the derivatives on uh, LHS and RHS, so on the RHS, this is what you will have. Then, uh, and then you can use this uh, uh, or or after a bit of simplification. Let's see. I'm taking this exponential I omega uh, t over 2. Then with that, what I'm having more is, so I have omega a naught uh, cos of uh, omega prime t by 2, then plus I omega by omega prime a 0 omega 0 minus omega plus b naught omega uh, sine, this is sine omega prime t over 2. Then you have plus I omega prime a 0 sine omega prime t over 2 plus a 0 omega minus omega 0 omega mi- plus b 0 omega uh, whole multiplied with this cos omega prime t over 2. So yeah, so this is what you have, after you take time derivative on the uh, first equation, you will get this. And then uh, you can use this a dot which we initially had, this a dot. So using this a dot, we can write uh, the LHSS I omega over 2 uh, exponential I omega t of b plus omega naught a, and the complete RHS which we have. So using that, like, you can collect, suppose if you collect the cos omega prime t by two terms. So if you collect cos omega prime t by two terms in the two expression, that like they should be equal, which means uh, uh, so you have to show that if, after when you like pick out the terms, you will get uh, you are basically have to show I omega by omega prime a 0 omega minus omega uh, plus d naught omega plus I omega prime a 0, and this that should be equal to minus I omega by omega prime b 0 omega minus omega naught plus a 0 omega plus I omega 0 over omega prime a 0 omega minus omega 0 minus omega plus b 0 omega. So with this, you can check here. I mean, you can simplify this, and you will find that uh, you will find this expression a zero omega minus omega zero minus omega square plus omega prime square minus big omega square minus omega zero square plus omega not omega equals to zero. So now if you use the relation which was given here, this omega prime, so using omega prime you can finally solve. So finally using omega prime you can prove that the I mean this is true, that this is should be zero. So with that you are telling that like if this is zero, basically you have compared uh, the uh, I mean you have compared this basically cos omega prime t by 2 terms, those are basically equal. So to prove that is equal, then this equation, the final equation which we have written down here, that should be zero. That means if you use the omega prime relation is given in the question, then that will be zero. You can check that. So with this, it says that like given a of t and b of t, they are indeed the solutions for the given Hamiltonian, where we have used the fact from the previous question where a dot and b dot are this, and we have that we have proved in the previous case here. So it's just a bit of rigorous algebra, but there's nothing more like involving here. So just we have to prove it. So there are two ways to do it. As I said, like first to decouple the equations, and I mean you can solve directly the coupled differential equation. That is by decoupling them and then solving the like the final uh, differential equations for a of t and b of t, which has their only their derivatives when you decouple them. So, so there you have to basically solve some second order differential equation, and the other way is to follow this. Take the a of t as the solution with the face value, and then take the derivatives of a of t. Take the derivative of the a of t expression which is given, and use the a of t derivative dA by dt previously which we have calculated, and using that you show that that is true. So yeah, then right. The next you have to show next. So yeah, next thing is to let's say if the particle starts out with spin up, that is uh, a0 equals to 1, uh, b0 equals to 0, uh, find the probability uh, find the probability of a transition to spin down. as a function of time. So you take E of t. I mean this. I mean you basically have to calculate U of t some probability that your final state is some chi of t, and, and your initial state is with spin up. So your initial state is spin up. So when this is your spin up state, this is what you have to calculate after some time t. Um, uh, right. Basically, I mean, uh, yeah. So to do that, like what you like, the question is basically asking you initially the given state that psi of t at t equals to zero, uh, at t equals to zero, you have a naught equals to one, which means psi of t, which we have. Uh, so let me write down this. Sorry, chi of t is basically a of t and b of t. So it is telling that chi t equals to 0, you have uh, uh, a0 b0, where a0 is 1 and b0 is 0. So that means you have upstate. This is your upstate. Then you have to find the probability that uh, yeah. So initially this is your state, and you have to find the probability of a transition to spin down. So you have to calculate the probability that this upstate will go to downstate. So so you can check that. Uh, let's take uh, uh, your A of t is given to be, so probably there is a uh, so what actually there's a small notation issue. What you have to calculate at the end is following. Uh, you have to basically calculate. Uh, you have to finally the final state should be downstate, and initially I mean, you have to calculate from this. This is the probability that you need to compute. So, and you can see that so your chi of t is if you take so if you check that, you will basically have to calculate p of t. Uh, you can write your downstate as 0 1, because your upstate is 1 0, your downstate is 0 1. So and your and chi of t is something a of t and b of t, and you take the mod square, then that is basically uh, b of t square. So this b of t square, then you can use the solution which is given b of t. Using that b of t, you basically have to take complex conjugate. I mean, you have to basically calculate b of t star b of t. Then that is, I mean, that will basically give you omega by omega. You just have to take the complex conjugate of b of t, which is itself given in the question, or just or which you will also prove. Like before, we have proved it for a of t. The same procedure you will prove for b of t, and indeed that b of t which is given in the question is your solution for chi of t, or basically the solution of Schrodinger equation. So and take the complex conjugate of that b of t, and multiply complex conjugate of b of t with itself with b of t. Then you will get this omega over omega prime square, then sine square omega prime t over 2. So yeah, so yeah, that is what you will be getting. uh, then finally, uh, right. Then next what you can, okay, then so yeah, we can quickly check again another case. An electron is at rest in a constant magnetic field. So this is for a constant magnetic field, not the one which we have seen for the time dependent magnetic field. So right. Uh, so for first thing, we can calculate the Hamiltonian. So let's do the Hamiltonian. Let's write down the Hamiltonian here. So again, we know we have, so yeah. So Hamiltonian, which we have been writing, so from that definition itself, or which we have seen at the beginning for a constant magnetic field, this is what you can write: h equals to minus gamma b dot s, where b dot is again. Uh, so yeah, this is not. I mean, this is time varying magnetic field, obviously. Like, I mean, not the constant magnetic field, but here you have only one component. So, you start from the definition of Hamilton, which we have started with our today's discussion. So again, Hamilton is minus gamma b dot s. So, uh, and you can see that your magnetic field is along your z direction. So you will only have your minus. I mean, you will only have. I mean, one component of magnetic field, and the other. There are three components of your spin vector for the electron. but it will be just minus bz and sj. So bz is basically, so if I write down this bs bz uh, kk, so and again you can write this as minus gamma b naught cos omega t sz. So use the poly matrix. Using polymetrics, you can write this as minus gamma e naught h over 2 cos omega t 1 0 0 minus 1. So yeah, that is what the Hamiltonian is. And then the next thing is to, if the electron at t equals to in spin up state with respect to uh, x-axis. So it is telling if the electron at t equals to 0 is spin up state with respect to x-axis. That means is uh, I mean Sx state is initially the Sx for the Sx operator. The spin state is uh, up, like for sz, the up and down state. So similarly, sx and xy, also like for sz, the eigenvectors are 1 0 0 1. So 1 0 is your up state and down state. So similarly there is for sx also. So with respect to x axis, then or that is, you can also write down as chi of 0, or maybe, so that is chi of 0 is chi plus x. Determine chi of t. You have to calculate what is chi of t. So chi of t in this case, you can, so let's first write down your sx. Sx is basically given as plus h by 2. That is your Pauli matrix 0 1 1 0, and its eigenvectors. So eigenvectors are basically chi of sx is 1 over square root 1 1, and 1 over square root 2 1 1. So this you can write down as up state with respect to x. This you can write down as down state with respect to x. So this is minus 1 here. So initially in the question it is given chi 0, chi at t equals to 0 is given to be uh, upstate with respect to x-axis. That is what it means. Upstate with respect to x-axis. So where so right, and here you can see your a0 b0 is initially 1 over square root 2. Then you have to calculate what is chi of t. If you consider k of t as a of t and b of t, then use Schrodinger equation again here, and using Schrodinger equation we can show chi of t dot is h chi of t, uh, that is equals to, you can write I h bar a of t a dot b dot equals to, uh, you can write this as Hamiltonian, which we have found here, this Hamiltonian multiplied with chi of t. So that will give you, so which you can write it as minus gamma b naught h bar over 2 cos omega t, uh, a of t and b of t. So there will be minus sign here. Okay. So now you can see you have two differential equation once again, a dot and b dot. So a dot is I gamma b zero over two cos omega t a, and then b of t is b naught over two cos omega t. So unlike the previous case, you see these two equations one and two, they are not a couple differential equations. You can directly, I mean, there's no uh, uh, complicacy here, which you can directly solve the differential equation one by one. So first, if you solve equation one, solve one, you can just simply solve by, as usual, like how you do variable separation. This is I gamma b naught or 2 cos omega t dt. This will give you, uh, if you solve this, ln a I gamma b0 over 2 cos omega t, that is sin omega t over omega, plus some constant, integration constant. And to get the integration constants, you have the initial boundary condition, that is at t equals to 0, a is 1 over square root 2. So using that, you can show your a is basically, uh, or a of t is basically, uh, 1 over square root 2, uh, 1 over 2 square root 2 exponential I gamma 0 gamma b0 over 2 b0 or sorry 2 omega sin omega t. And similarly, you can solve the other differential equation. You will have b of t, yes, 1 over square root 2 exponential minus I gamma b0 over 2 omega sin omega t. Then with that, you have chi of t. You finally have the chi of t as 1 over square root 2. Uh, yeah, that is exponential. Yeah, first you have plus I gamma b0 over 2 omega sin omega t, and exponential minus I gamma b0 over 2 omega sin omega t. Right. So that is your chi of t. So yeah, you finally got the chi of t. Uh, so now suppose the similar question is asked in this case, if to calculate the probability, find, let's say, find the probability of getting minus h bar over 2 when Sx is measured after time t. Yeah. So when Sx is measured after time t, you are, uh, I mean, what is the probability that you will get after time t minus h bar by 2? So uh, So basically, you have to again calculate something p of t as uh, down state chi of t mod square. That is the probability that which we seen in previously also. So yeah, and this uh, chi of t, remember this is an x with respect to x. That is what we have to. Uh, so that you can see uh, you uh, we have seen or in the previous bit which we said that for the given Sx Pauli matrix, this is your eigenvector, the downstate eigenvector. So you have to use that column vectors, that is 1 and -1. So for take if you take the complex conjugate, so that is basically taking the dagger, you will get uh, you basically get 1 over square root 2 1 minus 1, you will get a row vector. So then and your chi of t again, which we know before, this is your chi of t. So you just have to take the probability, which is modulus of 1 over square root 2 1 minus 1, and your chi of t is uh, 1 over square root 2 uh, exponential I gamma b0 over 2 omega sine omega t, then exponential minus I gamma b0 over 2 omega sine omega t, then this magnitude square modulus square, that is. So from there you basically get half uh, you basically get half exponential I gamma b0 over 2 omega sine omega t minus exponential minus I gamma b over 2 omega sine omega t magnitude square. So you can see, you can simplify this, or you can write this in the following form: I using the uh, sine Euler relation again. So which for sine x you can write this as, this is something which you know from your basic mathematics. You can write this exponential in terms of sine in this following that. So, so using that here, I can write this as I sine. You multiply I in the denominator and the numerator. So from there you get I sine gamma b0 over 2 omega sine omega t, and then again you take magnitude square. So that will finally give you a probability as sine square gamma b0 over 2 omega sine omega t. Yeah, so yeah, that is what your probability is. So right, so this is something which you will get for the final state if it is down state. Okay, so uh, okay, if there's any problem, if you would see uh, this problem solving, I mean, 1 second maybe from the uh, recording session, or maybe for the presentation note. If you have any issue with understanding here, just let me know, maybe in the next week, or anywhere, through email or whatever other means that we have. So we can talk about. Yeah, I hope you are also like taking your. I mean, uh, you are accessing your daily lectures, which are, uh, regularly uploaded to your NPTEL portal. So you can, I mean, you would be also like submitting the assignments along the way. Uh, is already, I think, week 6 is also out. So yeah, maybe a couple more weeks or something after that, you'll be having your test for this course, and yeah, that would conclude this course for you. So yeah, just try to stay tuned with all the updates that has been put up on your portal, and also your assignments. Try going through them, and yeah, it's just something you need to regularly tune to the things, so such that you do not miss out, because these things go in very sequence that anything you miss out in the middle becomes difficult to catch at the later end. So yeah, so and there are more things that will build on to this topic that we have discussed here, and also you have seen in your lectures as well. We'll see how, like, in a more general case, when we have this time dependent Hamiltonians, what are the ways we can tackle this Hamiltonian problems, how we can basically evolve the system. That is our major aim after all. So we'll see there are different techniques and methods in the coming session, maybe from next week onwards. Right. So probably for today we are almost on the time. So uh, it is done for today. So the time is up. We can uh, try to meet again next week, or any other questions. Please let me know, and uh, yeah, we'll see from there on. Like, whatever, if there is any problem or anything to discuss about any issue regarding this your advanced quantum mechanics course. So okay, that is for now. We'll see again. Thanks. Goodbye.